Hello, and welcome to Whoops, I Rewrote It in Rust. My name is Brian Martin. My pronouns are he, him, and I'm a software engineer at Twitter. Before we get into this talk, I want to provide a little bit of background about myself. I've been working at Twitter for 7 years and using Rust for 6 years. While I've been at Twitter, I've worked on a few different open source projects, including a benchmarking tool, a systems performance telemetry agent, and now I'm working on a cache server. Tail latencies are all super important to us. Typically for cache, we talk more in terms of P3 and 4 nines, but we care deeply about the entire tail. Outside of work, I'm currently a volunteer with my local search and rescue canine unit, and am training my dog, Riker, to find people who get lost in the wilderness. This talk focuses on distributed caching services. Memcached and Redis are popular choices in this space, and essentially it's a hash map over the network. I'm going to be focusing on simple key value storage, which is treated as volatile, meaning that items are subject to both expiration when the TTL is exceeded, as well as eviction under memory pressure. One of the main uses for this type of service is to protect databases and backend services by storing frequently accessed items and reducing the number of requests that a database must serve. That brings us to Pelikan, which was born from the desire to stop carrying a fork of both Memcached and Redis. Pelikan has a focus on performance and being able to reuse and compose various blocks of functionality to produce specific caching solutions. With its modular architecture, we're also able to introduce new libraries or re-implement some of these libraries and produce new or improved cache services. So, why was I working on Pelikan? Well, one of the things that was blocking our rollout of the C implementation was a lack of TLS support, and we wanted to be able to encrypt traffic between the client service and the cache. The project's primary author, Yao, now my manager, didn't have time to work on this, and I felt a lot more comfortable doing this type of work in Rust. So after some discussion, I convinced her that I should spend some time to work on a prototype. I wanted to be sure that in my Rust implementation, I was able to match the performance of the C implementation and make it an easy decision to migrate. There had been a couple of previous efforts which added Rust to Pelikan and made me think that this was going to be possible. Back in 2018, an engineer was trying to produce a new read-only cache-like service which happened to load data from the file system and provide it over the Memcached protocol. A new storage library was written in Rust and swapped into the existing framework, resulting in a C server with Rust storage. This was pretty cool, and the speed of development was really quite impressive, and it became the first commit of Rust into the Pelikan repo. The next engineer was a bit more ambitious and wanted to try and implement more of the core in Rust, but reuse the actual cache storage libraries from Pelikan, basically to swap out the server threads that were written in C with Rust implementations. Now, this was really exciting to me. It showed that we could do a lot more with Rust and Pelikan, but still reuse these well-tested C components. So first, a little segue on performance testing before we get too much further. I want to explain how we think about performance of caches. So we have two goals, really. We want to maximize our throughput and provide good latency. So when we are evaluating the cache performance, basically we'll tend to say that there's some latency threshold that requests must come under. We might define this at something like the P99 must be under 1 millisecond. And basically, as long as the cache performance is within that, as long as the tail latencies are within that, whatever throughput we get is great. But if at peak throughput we're exceeding that, we need to downrate it to the point where we rate limit the QPS and the latencies are coming in under this number. So basically, maximum throughput within a certain latency guarantee. So why do we focus on the tail latency? We're talking about P99s and P49s in the context of cache performance. Well, when we have a fan out of one, meaning there's only one request to the cache needed to fulfill some higher level request, only 0.1% of your requests are slower than the P39. Now, if you need 10 requests to load something like a user profile, now 1% of your requests are going to be slower than your P39. This gets even worse if you have a fan out of 100, maybe to load something like a home timeline. Now 10% of your requests are hitting that P39 or worse. Tail latency happens a lot more often than you think due to fan out. Okay, so we want to add TLS to Pelikan. We have this implementation of Pelikan Twemcache in Rust from 2019. It's Memcached compatible. It uses Tokyo with async for networking and uses the C storage libraries. So can we use this as a foundation to add TLS support? First, we need to performance test it. And unfortunately, I found there were some performance problems with this implementation. The throughput was 10 to 15% slower, which means we would need more instances to match the throughput requirements. 10 to 15% more expensive to run the service is quite a large number. Additionally, we were seeing that the tail latencies at P39s were about 25 to 30% higher, and this could actually lead us to start seeing timeouts and errors in production. This was going to make it a pretty hard sell. To visualize the performance, here we're looking at the latency curve of both the C implementation in blue as the baseline and the Rust implementation in red. We have the P39 latency in microseconds on the vertical axis and the rate-limited throughput on the horizontal axis expressed in QPS. And what we can see here is that throughout the entire range of tested throughputs, the Rust version is coming in with a higher latency. Additionally, we can see that the Rust implementation does not reach the same throughput that the C implementation does. So it's falling short in terms of throughput and is higher in terms of latency. So, I was thinking, well, Rust is a pretty fast language. Code written in Rust is performant. So can we do a little bit better than this? Can we take a few steps back and improve on this performance before we move forward? So before working on a full cache service, I wanted to rewrite the Rust Pingserver implementation. By a Pingserver, I'm talking about a simple ASCII ping-pong server. It's a really great starting point for proving out the performance of a design. It's a super simple protocol, there's no storage, just parse and respond as quickly as possible. It only knows two commands. It knows ping, and when it receives a ping, it sends back pong. And if it receives quit, it hangs up the connection. So again, we work on a Pingserver first to prove out the performance of our design and make sure that we have all the parts that we need. The Pingserver has all the same fundamental components that a real network service is going to have. It has buffers, it has a parser, it has metrics and logging, it has connection lifecycle management, and this was also going to be a place to add TLS support and make sure that the general framework for this was going to easily support both plain text and encrypted connections. I made some decisions based on past experiments and effort that I'd put into my other projects. I wanted to replace Tokyo, which is an async runtime, with a basic epoll loop provided by the library MIO. This would be closer to how the C implementation was done, and I felt like it was going to give me a better chance of matching the performance of the C implementation. I was also going to replace some of the C components with Rust implementations I'd been using in my other projects. If this didn't work out, I could always fall back to using the C implementations, but for a prototype this was going to save me time since I had implementations of these components in Rust and was already pretty familiar with them. And so once we had a Pingserver implementation, we benchmark it again. And here we're again looking at the latency curve of the P39 latency versus throughput, and the baseline is in blue and the Rust version is in red. And they're pretty much the same. So this looks good to merge, and we can move on to working on a real cache service. Great. So the next step is to work on Pelikan Twemcache, which is our Memcached fork within the Pelikan project. So since Twemcache is a Memcached protocol compatible server, we have a lot more complex of a protocol to work on. So I wanted to use a temporary storage library, and I basically just used the Rust standard library's hash map as a stand-in for the storage library. This allowed me to focus on the protocol parsing and handling, as well as the storage abstraction. And once I was confident that that was all working, I'd be able to switch over to the C storage library. But by having this sort of stand-in library, I was able to test the performance of the parser and all the other components that I needed for a real, protocol-compatible server. Once I did some benchmarking, it was looking pretty promising, and it was going to be time to switch over to the C library. This is going great. Of course, it wasn't going to be that easy. The deep integration of metrics and logging throughout Pelikan to get the observability we need would also complicate things. Since I had switched to the Rust-based metrics and logging, I'd need to either switch back to the C implementations of those libraries or try to allow the Rust version to work with the C libraries or vice versa, and I spent a lot of time fighting with this to come up with a solution. And that got me thinking about more and more wild ideas. Maybe I could rewrite it in Rust. So initially I didn't want to try rewriting the storage library in Rust because it's pretty complicated. We have a bunch of self-referential data structures, there's a bunch of memory allocations, there's linked lists all over the place, pointers everywhere, lots of unsafe code to write in Rust, and code that can be kind of difficult to write in Rust. So I spent a bunch of time fighting with this, and I thought, well, maybe we could simplify things a little bit. Maybe we could start with a single-threaded version of the storage library. That would make things a little bit easier. And maybe we could do only the hash table in Rust and leave the slab storage to the C version of the library, and we could do FFI bindings between Rust and C at this point. And yeah, maybe this would work. But this was also proving to be difficult. Luckily, around this time, there was a new research storage design that was written in C, and the design of this new storage library lent itself to being easier to port over to Rust. I actually simplified it even further and made it single-threaded only, so I didn't have to worry about any locking and all that kind of stuff that I would need for a multi-threaded concurrent implementation. Best of all, I was able to manage all the memory allocations in Rust, and this just made things a lot easier rather than doing any FFI between C and Rust. So, on the plus side, we wind up with something that is 100% Rust. And that really makes life a lot easier because we don't need to have CMake and Cargo working together. We can just use the Rust build tools. The rewrite of the code helped improve the overall design. There were a couple of things that I found while I was testing the the C implementation of this storage library, and I found a couple of places where I had some new ideas that improved the way the library handled some types of workloads. Then again, this cost me about 2 months of work, and it wasn't even 100% feature complete at the end of that. But I do think we got some benefits from doing a rewrite in Rust that we wouldn't have gotten if we did a rewrite in C. I think at the end of it, this quote from the main Rust lang page really summarizes it in terms of Rust empowers everyone to build reliable and efficient software. And I think this was really proved out through this whole thing. Rust allowed me to write something that was very high performance, And I was able to code with confidence in reliability due to all the nice language features that Rust has. Additionally, there are also lots of really great tools in Rust that really helped me through this whole process. One of the best things, though, was the zero-cost abstraction in Rust, which allowed us to express the code in a different way. At the end of the project, my manager, Yao, who's the project's primary author, sent me this little quote to include. And she says that the Rust implementation finally made Pelikan modules what they ought to be, but couldn't before due to the limitation of the C language. This feels exactly right and is just as fast. And I think that's really cool to hear from someone who's been writing C for a very long time, that, you know, there are all these really great benefits that we got from using Rust for this. That felt really nice. And to kind of illustrate that, showing here is the sort of modular structure of the code that we wind up at the end with the trait system and generics that are part of Rust. So we're able to express here that Segcache, which is the resulting cache server, is basically just the Memcached protocol with this seg storage library. And you can imagine that in the future, we'll be able to write another storage library or start using a different protocol in front of this storage library, and we'll be able to easily express how these things compose together. The resulting server, both the Pingserver and the implementation of Segcache, are only about 200 lines each for the actual server, and that's mainly to do some initialization and some boilerplate to express how these things are composed together. The rest of the code is all super reusable, and because we have a standard interface to a storage library, we can switch these things out pretty easily. Rust has some really awesome tools which helped make this a lot easier to work on. After fighting with CMake for a while in terms of Pelikan and having these hybrid C and Rust services in Pelikan, it really gave me a new appreciation for how great the cargo build tool is on its own. Additionally, there are these really awesome plugins for cargo, such as fuzzers and benchmarks, and these helped me have a lot more confidence in my code. I was able to use a fuzzer to make sure that the protocol implementation was rock solid, and I didn't have to think about every single edge case that I might encounter in writing a protocol parser. I was able to just simply run this fuzzer across it, come across some new test cases that I wanted to include in my code, and fix whatever bugs that I had. Additionally, these benchmarks made it easy to iterate on the protocol parser and the storage library and make sure all the parts were performing nicely. Then there were other tools such as Rust Format, which is an automatic code formatting tool, and Clippy, which is a linter. And these tools together helped me make sure that my style was consistent and that the code I was writing was idiomatic. And this made it a lot easier for both me looking back on parts of the code that I had written, as well as when it was time for Yao to review it, to make sure that the style was consistent. And to show what our end result was in terms of some benchmarks, here we're looking at the implementation of Pelikan Twemcache in C versus the resulting Segcache server in Rust. The Twemcache implementation in C is shown in blue, the Rust version in red, and again here we're looking at the P99 latency versus throughput. We can see at the end here that the Rust implementation doesn't hit the same throughput that the C implementation does. But it turns out that this is just due to the actual storage library itself, and the C implementation of Segcache has similar performance to the Rust version. So this is pretty good. Not everyone's running Pelikan though, so we can show up some benchmarks versus Memcache. And here we're showing Memcache upstream version in blue and the Rust implementation of Pelikan Segcache in red. And to sort of zoom in on the difference here, we can see at the upper end of throughputs that Memcache actually has higher latency than this Rust implementation of Segcache. So this is really cool. Memcache is really, really fast. So to see that we were able to write a Rust-based service that was just as fast, or maybe a little bit faster than Memcache, is really, really cool. So what are the next steps? The current priority is the path to production, but we also have this track of future work that we'd like to do, and maybe these can run in parallel. One of the first things in the path to production is going to be making sure that things are feature complete. As I mentioned earlier, even after 2 months of working on the storage library, I didn't have full feature parity with the C implementation yet. So there's more work that we need to do before we can move on to the next stage. There's going to be a lot more testing that we want to do. We have a whole suite of cache traces that we want to replay against this and make sure that it's looking as solid as it can with real cache traffic. After we're confident in our testing in a little standalone environment, we can move on to doing a production canary where we'll deploy one instance of Pelikan Segcache out into a cache cluster, and it will actually start receiving production traffic. After we've gained confidence through the canary process, we can move on to slowly rolling it out to prod, and then we'll have a Rust-based cache serving production Twitter traffic, and that's really, really, really cool. In terms of future work, one of the things that needs to happen is I need to improve the multi-threaded performance of Pelikan Segcache. And this is sort of a stretch goal, really. The Rust implementation of Pelikan Segcache in multi-threaded configurations does outperform our current internal fork of Memcached, especially when TLS is enabled. However, I like to win benchmarks, and so upstream Memcached does perform slightly better in terms of multi-threaded performance right now, and I want to see if I can close that performance gap. There's some additional optimization that could happen even for the single-threaded configurations. And this Segcache storage library, the segment storage library actually, doesn't allow us to replace the Redis backends yet. We still need a different storage implementation that will allow us to replace Redis with a Pelikan implementation that has TLS enabled. But we are going to do that in Rust. Additionally, there are a bunch of other really cool things that I want to play with, like IOU ring or maybe user space TCP, and there's all sorts of really cool stuff that we will be able to do with this new Rust version to start from. So to wrap things up, Rust can definitely compete with C implementations in terms of performance. We were able to see that we were matching the implementations of Pelikan in C, and we were able to just barely win against Memcache in single-threaded configurations, so that's really cool. Rewriting isn't free, and rewriting in Rust is not the right choice for every project. We just happened to be at a good spot with this project where it sort of started to make sense, and we got a lot of benefits from doing this rewrite in Rust. We're on track for production deployment. Hopefully towards the end of the year, we'll start serving production cache requests with this Rust implementation, so that's really cool. And I think that Pelikan has a really exciting future with Rust, and this initial implementation is sort of paving the way for us to actually replace all the C code in Pelikan with Rust. So that's super exciting to me. I'm glad to see Rust being able to function really nicely in this space, and I think it's going to be really good for the code base. Thanks for listening to my talk, and thanks for all the people involved in putting together this conference. Feel free to reach out to me on Twitter with any additional questions that you might have. Bye.